Hi, my name is Julian. I'm a PhD student in the ABS laboratory at the University of Colorado Boulder. And today I'm showing some of the work we've done on the effects of debris attitude on the electrostatic tractor performance. Let's start with a quick overview of the motivation of the electrostatic tractor. The electrostatic tractor is an active debris removal method that aims at touchlessly reorbiting debris or retired satellites from geostationary orbit to a graveyard orbit. And the way it works is that you have an electron gun attached to the servicing satellite, and the electron gun is aimed at the debris. Due to the emission of electrons, the servicer will charge positively while the debris will charge negatively. And that results in an attractive electrostatic force between the two spacecraft. And using inertial thrusters, the servicer can then pull the debris to a higher orbit, like a graveyard orbit, 300 kilometers above geostationary orbit, for example. We use the multisphere method to approximate the electrostatic force between the two objects. The multisphere method uses several spheres that are distributed on the surface of the two objects. And knowing the potential, the electrostatic potential of each object, we can then approximate the charge distribution and consequently approximate the electrostatic force and torque that acts on each spacecraft. For the relative motion control, we use a spherical coordinate frame, and the required thruster acceleration consists of two terms. The first term is the feedback term that feeds back on the relative velocity and position of the two spacecraft. And the thruster acceleration also consists of a feed-forward term that depends on the estimated electrostatic force between the two spacecraft. For this analysis of the debris attitude effects, we consider three different categories. The first category deals with prescribed attitudes. That means that we basically hold the debris at a fixed attitude or at a fixed orientation, and then we simulate the reorbit process. That allows us to identify those debris orientations that minimize the required reorbit time and control of effort of the reorbit process. The second category deals with freely rotating debris. So instead of holding the debris at a fixed orientation, we use the rotational dynamics to simulate the reorbit process with a generally rotating debris that is subject to electrostatic torques, for example, as well. And in this category, we also perform a Monte Carlo simulation to see how those rotational effects of the debris, how they affect the reorbit process and the performance of the electrostatic tractor. The final category deals with electric potential estimation errors. So previous work found that the relative motion control is somewhat sensitive to estimation errors of the electric potential of the debris. And with this last category, we want to combine the effects of potential estimation errors and attitude effects and see how that affects the reorbit time and the control effort. So for the first analysis, we look at prescribed attitude. So we hold the debris at a fixed orientation, and we change that orientation through all the simulations using a pitch and yaw angle of the debris satellite. As you can see in this graph right here, is that there is one orientation, for example, at a yaw angle of 0 and a pitch angle of -90 degrees, where the reorbit time is significantly reduced to only 40 days. And that is a result of the basically closer distance of the two centers of charge of both spacecraft, because this orientation corresponds to that orientation where the solar panel of the debris is pointing toward the surfacer. And if the solar panel is pointing toward the surfacer, the effective distance between the two center of charge of each spacecraft is reduced. And therefore, the electrostatic force is stronger, and the surfacer has to compensate more for that and use a higher thrust. And that, as a result, leads to a decreased reorbit time. In the right graph, we see the required delta V for the reorbit maneuver, which is altitude raise of 300 kilometers. And in general, the delta V requirement is not affected as much by the debris attitude as the reorbit time. And also, it's worth noting that the delta V might seem a little bit high with 27 meters per second for a 300 kilometer orbit raise maneuver. But you have to keep in mind that the servicing satellite is not just raising its own orbit, it's also pulling another spacecraft with 2,000 kilograms. So that increases the required control effort. The next analysis deals with freely rotating debris. So instead of holding the debris at a fixed orientation, we simulate the reorbit process, including the rotational dynamics of the debris. Generally, the debris will start tumbling due to the electrostatic torques that act on the debris. So the two graphs show the maximum angular velocity and the average angular velocity as a function of the initial orientation of the debris. But now the initial orientation is not held fixed, but the debris will generally start rotating. And as we can see, there is, again, this orientation at a yaw angle of, the initial orientation with a yaw angle of 0 degree and the pitch angle of minus 90 degree, where the debris doesn't tumble much. Like the rotational rate is very small during the reorbit process. And this orientation is, again, when the solar panel of the debris is pointing toward the surfacer. And that can be illustrated in the following way. We use the multisphere method to approximate the electrostatic force and torque that acts on each spacecraft. But we can also replace this, this model with a single sphere model where one sphere is placed at the center of charge of each spacecraft. And in general, the center of charge of, for example, the debris will shift towards somewhere at the solar panel because charge accumulates at the solar panel. So the center of charge is located somewhere here, for example, at the solar panel. And that is an offset with respect to the center of mass. Consequently, there is a torque acting on the debris. Now, if the center of charge was to lie on the line that connects the two center of mass of the two spacecraft, then the force, the electrostatic force, basically wouldn't have any leverage, so there is no torque. And that's exactly when the solar panel of the debris is pointing towards the surfacer. So in that case, there is no high rotational rate. We also performed a Monte Carlo simulation of the reorbit process with 100 runs, and we randomized the initial orientation of the debris and the initial angular velocity, both magnitude and direction. But the magnitude of the initial angular velocity is bounded to between 0 and 10 degrees per second. As we can see there, the reorbit time and the delta V requirement basically average out. So even though for all orientation, if we held the orientation fixed, we saw reorbit times between 40 days and even above 100 days. But if the debris is rotating, then this averages out to a value of about 78 days. And the delta V requirement also averages out. So that basically means that with rotational rates, if the debris is rotating or tumbling, then you won't achieve any really quick reorbit, but it also doesn't take too long. For the last analysis, we look at the uncertainty in the debris electric potential. So previous work found that an estimation error of the electric potential of the debris can significantly affect the relative motion control. And that is because the relative motion control feeds forward the estimated electrostatic force, but the electrostatic force depends on the electric potential of the two spacecraft. So if you have uncertainty in the potential of the debris, for example, then you will also misestimate the electrostatic force. So this graph shows how estimation error of the electric potential delta phi of the debris affects the equilibrium separation distance between the two spacecraft. So if you had a reference distance of, let's say, 20 meters, then if you underestimate the electric potential of the debris, the servicer will actually pull away further and settle at an equilibrium distance that is greater than 20 meters. But on the other hand, if you overestimate the electric potential, you basically underestimate the electrostatic force, and the servicer will come closer to the debris. And at some point, there is a critical point. If the estimation error is greater than this critical point, for example, here at 10%, then there is no positive equilibrium solution anymore. So this essentially means that the two spacecraft would collide. So we performed another set of Monte Carlo simulations with 100 runs, but this time we included a normal distributed estimation error of the electric potential of the debris. So if we look at the separation distance of the two spacecraft, we can see that the spacecraft doesn't, even though it's supposed to maintain a separation distance of 20 meters, it settles to 22 meters, for example, if the electric potential is underestimated, but it also sometimes settles to a separation distance that is closer than 20 meters. Now, the reorbit time and the delta V requirement are similar to the results with no estimation error. But one thing that we found is that there are still some cases where the two spacecraft collided. That means that you had an estimation error that was above 10%, for example, and the rotational rates do not completely eliminate the sensitivity to estimation errors. So even if the debris is rotating, an estimation error of the electric potential can still cause a collision. So in conclusion, we found that some debris orientations minimize the reorbit time and the delta V requirement during the reorbit process. And those orientations are general when protruding structures such as solar panels, for example, are pointing toward the servicer. We also found that the delta V requirement is not affected as much as the reorbit time. And this motivates research on how to detumble a debris and also hold it at a desired orientation. Previous work has only shown that it's possible to hold a debris at a fixed orientation using electrostatic torques for cylindrical objects, but no general 3D shaped objects such as this satellite, for example. We also looked at freely rotating debris and found that the electrostatic torque generally causes the debris to tumble, but the rotational rates average out the reorbit time and the delta V requirement. And for the electric potential uncertainty of the debris, we found that the sensitivity to their electric potential estimation errors is reduced, but not completely eliminated. Thank you very much, and please feel free to reach out if you have any questions.